when the bar swings downwards and hits the ball, it imparts momentum to the ball. And this inherently is a collision. However, to understand the collision part of the problem, you have to understand how much momentum the bar has just before the collision. So there's a part of this problem that's missing in the picture. And that part requires that you consider there's an instant just before the collision where the bar is moving, but the ball hasn't been struck yet. You need to figure out how fast the bar is moving just before it strikes the ball. And that's a problem we did last week. And so that's a conservation of energy question. So there's conservation of energy from here to here, and then conservation of momentum from here to here. So you need to rethink maybe the order of the problem. Now, I will tell you that this is going to be 4.5 radians per second right before the collision. That's the intermediate answer you're looking for. If you get something else, you've made a mistake. So Benson, what kind of energy does the bar have before it swings downwards?
Potential,
Gravitational potential. Can you tell me how I would calculate that?
You do mgh equals 1/2.
Well, just the left side.
Oh, yeah, just mgh, and h would be 0.75.
0.75. Can you tell the class why it's only half the length of the rod?
Because that's where the center of mass is.
Excellent. So the center of mass of the rod only descends to a position that's 0.75 below where it started, so its gravitational potential energy is going to be based on just half of the length of the rod. Okay. Daniel, can you tell me what kind of energy this has after it swings to the bottom? Why doesn't it have translational kinetic energy? Can you tell me the conditions to have translational kinetic energy? There are two that must be met. The center of mass has to be moving, and you said it just a second ago. No, but it has to have a fixed pivot point. So those two conditions have to be, for it to have translational kinetic energy, center of mass has to be moving and it can't have a fixed pivot point. So the reason this one doesn't have translational kinetic energy is because it has a fixed pivot point, and therefore it can only have rotational kinetic energy. There's two conditions to have translational kinetic energy. The first is the center of mass of the object has to be moving. The second is it can't have a fixed pivot point. So like something that's rolling, the pivot point's moving the whole time. All right. What's that? Rolling would have translational and rotational. But if I throw a football, right, it's spinning. It's got an axis of rotation, but the axis of rotation is moving along with the object. Mm-hmm. But this bar, even though the center of mass is moving, doesn't have translational kinetic energy because the pivot point is fixed in space. Yeah. What am I going to use for the inertia? Lynn? 1/3 ml squared. Thank you. All right. You set these equal to each other. I know you guys tend to like to put the numbers in. I would have encouraged you not to. Because if you set these equal to each other, you just find that omega squared equals 3g over L. And I know you guys love your calculators. Please stop using them for just a couple of steps. Because although you guys are calculator masters, on tests more than once, I've had to point out to you that you can't use your calculators right. You make mistakes with them. And that's a pretty ubiquitous thing around the room, because we've all made these silly mistakes that make you frustrated. A lot of it can be clarified by just using your calculator. 3 times g is 30. You're going to divide 30 by 1.5, right, which is just 3 halves. So that's 60 over 3, or 20. So the square root of 20. And you guys can tell me the square root of 20, can't you? Without using a calculator. Even if you didn't know it, you would know it has to be between 4 and 5, right? 4 squared is 16, 5 squared is 25. I'm pretty sure it would land right in the middle. 4.5 is a good bet for the answer there. Try not using your calculator so much. You guys, we are becoming less able to think on our own. Now, the next part of the problem is the part that's actually new and requires something that we talked about on Tuesday. Now, that part's a little bit tougher, but not impossible. This is a conservation of angular momentum question. So now that you have this part, please see if you can figure this part out, how fast the ball is going. Most of you have. So I'll give you 60 seconds before I start calling people out on it. So we're going to do the collision part now. Collision part is a conservation problem as well. So I'll take a volunteer. So you want to tell me where to start? Go ahead.
Don't you set the rotational energy of the rod equal to the translational kinetic energy of the ball?
No. I don't think that's going to work. And here's why. I don't think the energy is going to be equal. I think there's going to be loss of energy because this is a collision. And most collisions are inelastic. I expect that there'll be some kind of energy loss during this collision. So there's also a couple of reasons why I think we can say that the energy is lost, but let's not dwell on that. The question is momentum lost. Collisions are almost always surrounding momentum. In fact, we derived a bunch of stuff about momentum to use it in collisions. Momentum is conserved because in this case, the ball doesn't cause a torque about the pivot point of the bar. The ball causes a torque about the pivot point of the bar, changing the bar's momentum. So there's a change in momentum of the bar due to the collision with the ball. That collision applies a force to the ball, but it's a torque relative to the bar. Due to Newton's third law, there has to be equal and opposite torques applied here. So there's an increase in momentum for the ball due to the same loss in angular momentum from the bar. But I don't know about the energy. In fact, I'm going to ask you about the energy after we figure out how fast the ball is going. So why don't we start by you telling me how I would calculate the angular momentum of the bar? It is I omega. But now we have to deal with the ball. The ball is going to be a little bit harder, I think. So, I don't know. Anthony, what do you think? How would you calculate the angular momentum of the ball?
We have to, if you set up with the moment of collision, they're both going to have like the same angular momentum since it's inelastic.
Okay. I agree that their angular momentum have to be equal because it's a collision. So the ball has angular momentum, but we can't calculate it as I omega because it's not rotating. It's traveling in a straight line. So we're going to have to use the angular momentum for a point mass traveling in a straight line. And we're going to measure its angular momentum relative to the pivot point of the bar, since it's the interaction with the bar that we're actually trying to study. So there will be angular momentum for a point mass, which technically is r cross p, where r does represent a torque arm in this circumstance. Where the torque arm is really where the ball is moving relative to the bar, and that is this length L. Now, the bar has a mass of 50 grams, and the ball has a mass of 25 grams. So I'm just going to put a 2 here and put an M here. That way I have less math to do. That's why I gave you 25 and 50. Fair enough? Now, the angle, that's a pesky one, but it's 90 degrees because we are at the instantaneous moment where the ball is leaving the bar. Now, a few moments later, this angle is going to change, but the angle is going to get bigger, but the R is going to get smaller. I'm sorry, the R is going to get bigger too, but the sine of the angle is going to get smaller. And we talked about the fact that that ratio will preserve the angular momentum as it moves away, so we'll have a constant angular momentum relative to this position. See last week's lecture. So I think we're kind of done with the math there, right? We can do the work here. It's not much to do. I'll cancel out one of the L's. I'll cancel out the M. And sine 90 is 1. So it looks like I have 2/3 L equals V. And considering, I'm sorry, I forgot the 4.5. Considering L is 1.5, 2 times 1.5 is 3, and 3 divided by 3 is 1, so there are lots of variations to this question. And so let's just talk about 2 variations. One of them is the bar was stopped in this problem. But what if the bar kept moving, swung upwards a little bit? We did that problem first semester. You should check your notes. But we didn't have physically rotating objects first semester, so we just had a box on a string. If you recall, the box on the string hit another box that was at the edge of a table. But the box on the string kept swinging upwards a small amount. You had to figure out by how far it swung upwards how fast it was going after the collision. That adds a layer of complication. Another layer of complication is just put this at the edge of a table. Why not? Have the ball come off the edge of the table. Now you've got a projectile problem too. So just keep in mind there's lots of variations. Or just have the ball stick to the rod. That makes for an interesting question because now the center of mass of the system has changed. So don't think we're looking at the hard version of this problem. We're looking at the basic version of this question. The only thing that's unique about it is that we use gravity to provide the energy for the bar. You should, on your own time, show how much energy was lost. There was energy lost in this collision. You should compare the energy the bar had before contact, MGH, with how much energy the ball has after contact, and show that there's energy lost, that it's an inelastic collision. But that's an exercise, so I would like to talk about a different question. Let's take the same bar, same mass, same length. Let's take the same, I'm going to say ball, but let's change it and make it a flat ball, a puck. And let's say that we're looking down on it. So we put this all on the air hockey table. We're looking down on it, and the puck is being fired at, we'll just say it's got that same speed, 4.5 meters per second. And it's going to strike the rod. And the question is, after the collision, what is the velocity of the rod? But let's also say that after the collision, the puck bounces off of the rod with a speed of 1 meter per second. What happens to the rod? Now, this isn't an energy question. This is a strict momentum question. And this was in your homework, actually. So hopefully you've taken a look at your homework, because I asked this question like 6 different ways. And we're going to do one of the ways right now. There's no numbers in it. It just asks you to try different stuff. This one's not terrible, but there are several variations on this question. The first variation is to have a fixed pivot point someplace in the problem for the rod. That's a variation. That's fine. That's probably the simplest version, because after the collision, you're going to have clear motion and you're going to understand how it moves. I don't want to do that one. I want to do the one where there is no fixed pivot point, where the rod is free to move. In this problem, the rod's center of mass is going to begin moving after the collision. In fact, if you remember first semester, this is just a one-dimensional collision when we think of it from the point of view of the center of mass. So this bar is going to have a velocity in this direction. Yep. Looks like it's going to have translational motion after the collision. It has to. The system had translational motion before the collision, so there has to be translational motion after the collision. There's nothing to stop the bar. There's no force on the bar to keep it in place. Yes?
Is this the same bar as the last question?
I did say that already. So there's more than that, though. Where the ball strikes the bar matters. If the puck. If the puck was striking it at the center, that would be no big deal. But because the puck is striking it at the edge, it's clearly going to provide a torque on the bar during this collision. And that's an unbalanced torque, so there'll also be a rotational velocity of the bar after the collision. So tell you what, I'll take it easy on you. Do the first problem. Find this V. That's a first semester one, and you all should be super successful there. We'll find out in about 60 seconds. I just want a numerical answer from one of you. Answer. 2.75, that's right. That's how fast the bar will be traveling after the collision. And that's just using linear momentum. That's all you need. So 2.75 meters per second. And I know there's like 4 people, based on what I saw, don't have that. That's too bad. The only thing with momentum before the collision is the puck. After the collision, the bar and the puck both have momentum. That's it. Just like before, I'm going to do everything in terms of m. And here's where some of you might make a mistake, but make sure you remember that velocity is a vector quantity. When it bounces off, it's going to have a velocity in the other direction. That's negative. That's it. So you guys can do arithmetic. But now you need the rotational speed of the bar. And there are some things here that are worth noting. The bar is going to begin spinning, and that part isn't critical, it's not hard to understand, but you do need to remember a few things. First, the bar doesn't have a fixed pivot point. Because it doesn't have a fixed pivot point, objects naturally revolve about their center of mass. So when you're dealing with the moment of inertia now, you're going to have to change where the center of mass, or where the moment of inertia is measured from. Because it's not pivoting about the edge, it's pivoting about the middle. But also, you have an object with angular momentum before the collision. And then after the collision, you have 2 angular momentums as well. Because the ball is moving, it has angular momentum. In fact, it has angular momentum in the opposite direction. That part doesn't change, right? Because the bar is spinning, in this case, counterclockwise, but the ball is traveling with a counterclockwise angular momentum relative to the pivot point. But also, you have to keep in mind the pivot point before the collision. This is what's going to be r. Not the length of the bar, but when we calculate the angular momentum of the ball, it's relative to where it's going to rotate after the collision. So when we go to deal with r times mv times the sine of the angle, r is going to be the length of the rod over 2 times m times v. Your bar, on the other hand, 1/12 ml squared still, but because I'm doing everything in terms of L, you'll forgive me if I just put 2m here, L squared, times its speed. That's still just I omega. But I have to deal with the puck still, and the puck is going to have its angular momentum, which is still L over 2, because that's still relative to this distance, times m times -1. And I'm leaving out the sine of 90. That's it. That's how you find omega. And that part's arithmetic, and I'm kind of done waiting on arithmetic today. You guys can do arithmetic. This is the basic version of this problem. And I'm not trying to say that to say, oh, I can make them really hard if I want. No, I'm saying there are lots of varieties of what this problem looks like. This is just one of them. This is basic in that the ball is striking the very edge of the bar. Of course, you can imagine a problem in which we take the puck and put it someplace in the middle. That doesn't change the problem much, but I would expect that it would rotate less if I don't strike it at the very edge. Right, the further away from the center I strike it, probably the bigger the rotation will be. And I know that there's an extreme case where if I just make it hit the center, there'll be no rotation at all. But if you want to really see this problem in action, you have to imagine the other case of this problem. The one in which the puck actually sticks to the rod. That's a much different question. Probably for reasons you haven't thought of all the way. If the puck sticks to the rod, so that's what we have for a collision. So we have this before case, and then we have this after case. Is it clear to you that the center of mass of the system is going to change? You'll have to know where that center of mass is before the collision if you want to figure out how much angular momentum the puck has relative to the bar, right? Because it's going to rotate not about this position, but by a position closer to the two things. So there'll be a shift in the center of mass. Also, this changes the moment of inertia of the system. So when you consider what L is going to be, you'll have the combined moment of inertia of the bar and the puck, but it's going to be rotating about wherever the center of mass of the system is. So not only do you have to calculate this combined moment of inertia, you have to find out the moment of inertia of the bar at a position that's not the center of mass. So you have to use the parallel axis theorem. This is an incredibly complicated question with lots of moving parts. Having the puck bounce off is almost always going to be easier than stick to. And I know we found first semester that when objects stuck to each other during a collision, they were relatively easy to deal with. Lots of things change under the circumstance where there's no fixed pivot point. Now, if the pivot point's fixed, all those things I just talked about aren't nearly as hard to deal with because we don't have to change where the axis of rotation is. But when it sticks together, the axis of rotation changes, and that makes a big change in your problem, which is why it's one of your homework questions. You should play around with it a little bit. I don't give you any numbers to use, but if you want, put some numbers in there if you think that'll make it easier. But I think you should also consider just a variable location of placing the puck in different locations and having it strike the bar.